Right, so in this video, we are going to discuss the last subtopic for chapter 3, which is 3.6 exponential growth and decay. So previously we have discussed 3.1, 3.2, 3.3, 3.4, 3.5, and today we're going to sort of like incorporate every single thing that we have discussed before and use the concept in order to discuss topic 3.6. Right, so for exponential growth and decay, so there is a specific equation that we can use to model the situation. So it says over here, in many natural phenomena such as population growth or radioactive decay. So growth means like how the population grows. Like for example today, the people in Malaysia is like, for example, 3 million people in Malaysia, and in the next 10 years it would be 10 million and so on. So that is population growth. And in terms of decay, what is decay in Malay, by the way? In Malay, decay is report. Like, you know that, like what happened to radioactive over time is that, as you live it over time, so radioactive components, they will decay. Decay means like the amount will become less and less after time. So that is called as being decay. So basically what happened for growth is that, so the amount increase. So this is what it means by growth. So amount increase, and when we have decay, so what happened is that the amount decrease. So this particular equation that we are about to see, so we can actually use it to model both cases for which we have something which the amount is increasing and something for which the amount is decreasing. Okay, so if you have a quantities that grow or decay at a rate proportional to its size, so this is going to be the equation that we can use. Okay, so this is rate, so dy over dt, anything that is written with respect to t is going to be the time, so that is called as being a rate. So in terms of the equation, so this is going to be the equation that we use to model this, the quantity grow or decay at a rate proportional to size. And this symbol over here, so this actually means proportional. Okay, and this is rate of change of size. So here, because it's going to be size over amount, because what happened is that we're going to declare y as being size or amount of something. So that is going to be y. So when we have dy over dt, so it means the change of y over time. So what happened to y as it changes as time increases. Okay, and that is going to be proportional to the y by itself. And of course, so when we have a proportional symbol, which is what we have over here, so this is our proportional symbol, so we can replace that with an, so I actually replaced that with an equal here. But what happens is that when you replace a proportional symbol to an equal, so you have to add a proportional constant, and this k over here is actually our proportional constant. Okay, and this k value for our case, so it could be positive value, it could also be a negative value. So what happens is that when k is a positive value, so k is greater than 0, so that is when you have a growth situation. So when something is growing, then your value of k is going to be a positive value, so it's going to be greater than 0, positive value. And on the other hand, when your k is a negative value, so it's a value that is less than 0, meaning that it's going to be a negative number. So what happens is that it is a decay situation. So whatever that y that we have in the scenario, so the y value is actually decreasing. So that is called as being a decay, and your value of k should be a negative value, then only it is possible to happen. So basically, so the equation that we're going to solve here is going to be this equation over here, so which is dy over dt is equal k of y. Okay, so let's have a look at the solution. So I have dy over dt is equal k of y, and when we want to solve this equation, so basically if I solve this, so what happened is that I will get an equation in terms of y. So we will get equation in terms of what I have at the top over here, and for this case it's going to be y. Okay, what happened is that, so how do we get this equation from the equation that we have seen before? How does the dy over dt equal ky becomes y of t equal y naught exponential of kt. So you will learn this later in your third mathematical course, which is applied mathematics. I'm not going to explain this here. So this is called as an ordinary differential equation. So there is a specific way that we have to use in order to solve for this, and this is not in your syllabus. You haven't learned any and you haven't seen anything like this yet. So I'm not going to explain this in detail, but later you will come across this in applied mathematics that you're going to take after calculus. Okay, so basically in this in this course, so we will be talking about the solution over here, for which yt is equal y naught exponential of kt. So let me add another page for which I will just explain about this equation. So we're going to be dealing with this equation. So y of t is equal y naught exponential of kt. So this will be the equation that we're interested in. Let me put it in the middle so I can explain that to you easily, each of the component. Sorry, that should be yt. Where's my equation just now? Why does it disappear out of the blue? So here. So this is going to be yt is equal y naught exponential of kt. So let me explain to you like every single component in detail. So let's first talk about the yt. So this yt over here, so this is pronounced as y of t. Okay, so it's not y multiplied by t. So y of t, so it doesn't mean y multiplied by t. No, it doesn't mean that way, but it's called as y of t, meaning that y is dependent on t. So what does it mean by y is dependent on t? So that means that whenever t changes, so y changes as well. So that is what it means. Okay, so it's been pronounced as y of t. So the value of y, it depends on t. Whenever we change the value of t, automatically the value of y is also going to change. And so that will be the first component. So the second component that I would like to introduce to you, so will be this one, which is y naught. So what does it mean by y naught? Okay, so if y of t means that it's got to be y at time t. So this actually means y at time t. So that is what it means by y of t. And y of naught means that y at t equal 0. So this is called as the initial value. This is the term that we use. So it's called as initial value. So basically, it's just telling you what is going to be the value of y. So when t is equal 0. So y when, so I've written over there. So it's just like what is going to be y when t is equal 0. And it's called as being an initial value. So initial value is not a variable, it is a number. And you will get the number in the equation. So let me put a remark over here. So this will be a number in the equation. Okay, and of course the e over here, you have seen this multiple times. So this is going to be exponential, and the power of the exponential is going to be exponential of kt. And we have seen k before, so k is actually a constant value, and the idea is still going to be the same. What happens is that when k is greater than 0, so this is going to be for the case of growth when the amount increases, and when k is less than 0, a negative value. So this is going to be the case that when we have a decay scenario, when a value is decreasing. And of course, what is going to be t? So t for this case actually represent time. So t will be time. Okay, and in this equation, I would like to highlight to you so the fact that there are only two variables. So what are the variables in the equation? So the variables in the equation are only y and t. So y represent the amount, t represent the time. So y, this is going to be amount, and t will be time. Okay, what about the rest? So the rest, so which for here, which is y naught and k, so they are not variable, so they are constants. So constants mean numbers. So how do you find the numbers? So either it will be given in the equation, or there will be some information given in the equation that will enable you to find what is going to be y0 and what is going to be k. And in terms of the variable, when we write the equation, we simply copy it down. But for the case of y0 and k, so when you write this equation, you have to find, so what is going to be the value of y0 and what is going to be the value of k. When you have these two information, then only you can use the equation. So it might be kind of very unclear still. How are you going to use this equation? So let's have a look at an example. So this is not yet the example. So this is called as the half-life theorem. Okay, it says over here, suppose a quantity grows exponentially. So quantity over here referring to the y. So let's say we have an amount that grows exponentially. So then the doubling time of the quantity, so y become double, so which is going to be 2 multiplied by y. Okay, let's say the doubling time. So doubling time is like how do I explain this to you? So there's going to be the time. So doubling time. So doubling time. It's already there. What is doubling time? Doubling times is the time it takes for the amount for y to become double. Okay, and what does double means over here? So double means twice the initial value. So that is going to be twice of the y0. Remember, y0 is our initial value when we begin the process. So what is going to be the value? So that will be the y0. So doubling time means that the time it takes for the y0 to become twice the amount. So it's going to be, so if you want to know what is going to be the time it takes to become twice the amount, so this is going to be the formula that you're going to use. So T2 is going to equal log 2 over k. So why is that so? So let me add another page over here so that I can explain this to you. So our equation that we have seen before is given by this. So yt is equal y0 exponential of kt. So now what we want to know is that, so what is going to be the value of t when y is equal twice of y0, when y become twice the amount of the initial value. So now all we have to do is, so we're going to substitute. So the t, that is what we're interested in. So we're going to find what is going to be this value. So when we already know what is going to be the value of y. So what is going to be the value of y for this case? So for this case, the value of y is going to equal twice of y0. So that is going to be the value of y. And then I'm going to copy everything down. So y0 exponential of k. And then t over here. So this is what we want to find. So just simply copy it down. So it's going to be t. So now what I'm going to do next is I'm going to divide both of the equation by y0. So I'm going to divide left and right by y0. So for which my equation is now going to be 2 is going to equal exponential of kt, because so both of this are going to disappear. And remember, for this case, what we wanted to find is we wanted to find the time. So t, what is going to be the t? And in order to do that, I have to get rid of the exponential. And I did mention this to you like a couple of times. How do we get rid of the exponential? So we can only get rid of the exponential by taking a log with the same base, which is going to be log e. And we know that log e is equal ln, so we have to log both sides of the equation. But we cannot log only this side and leave the other side as it is, no. So when you have an equation, whatever that you do on the left hand side, you have to do the same on the right hand side. So I'm going to log both sides of the equation. Let me write this as exponential kt is equal to, so now we're going to log both sides of the equation. So log of exponential kt is going to equal log of 2. So these two, they're going to cancel each other. So I'll end up with kt is going to equal log of 2 and t is going to equal log of 2 over k. So meaning that, so when the amount becomes twice the initial value, so how long does it take? So it's going to be a formula of log of 2 over k. So that's the formula that we can use. Okay, so that's going to be in terms of, so this theorem over here. So now let's have a look at an example.